Hi, I'm Professor Jay Lee from University of Cincinnati. This section is about Industry 4.0 transformation and comparison of Industry 4.0 with today's factory. I will talk about the three topics, and first I'll introduce the data to knowledge in manufacturing environment, how we look at the data, its meaning, and what's an evidence-based approach versus experience-based approach. Then we will review the manufacturing transformation in Germany, Japan, and the United States, so we can understand why and each country is pushing for the transformation. The third, I think we can do a comparison because we have to know the difference between today's factory versus a Industry 4.0 factory. First, let's look at data to knowledge in manufacturing environment. This chart shows typically when we look at a problem, for example, in a factory, we have a problem. The problem could be defect, could be quality, could be efficiency. Over the years, we continuous learning. Eventually, we gain the insights, wisdom that become our knowledge or experience. It takes many years. Unfortunately, when people retire, many of these experiences get lost. Now, the issue is we don't have a logics to give to next generation. So what the role of data is to build the logics and relationship between some issues. So eventually it became a evidence. So from here, I can say each country treats this problem differently. For example, when we look at the data to knowledge, the true value is how we gain from the knowledge so we can redefine the problems. Sometimes we can avoid the problems. That's what really is about the wisdom. But when we define the craftsmanship, for example, Japan, in Germany, there's some difference between how they define things. US, early years, how to define the craftsmanship. The craftsmanship is about how to make problems and then eventually train the people, the worker. The worker can continuously learn and making a perfect or a customized or a very a unique products and become their knowledge and give to next generation. We can see many countries still remain that. Now the machinist is different. Machinist is basically look at the problems, then to design a machinery to solve the problems. So when problems are solved, then eventually the machinery actually carry that knowledge. And unfortunately, if after many years later, and many people didn't understand why the machine was designed. So the two differences between craftsmanship and the machinist is about how we give to the knowledge to train people versus to make machinery. Now today, I think more and more so, we have to understand why problem occurred, what's the relationship between the problems with the issues. So I think we need to start think how to avoid the problems. By doing that, we can formulate a relationship to make experience-based manufacturing to evidence-based manufacturing. That is what we are talking about, data to knowledge. We believe this transformation is very critical for the future smart factory. Because in smart factory, we need to have a system, and that could be a machine learning algorithm, could be a predictive analytics tool. They can help people, help the machine to avoid problem, so we can predict and prevent and reconfigure. That's really a true meaning of a smart machine. All right, the second, let's look at the manufacturing, why each country transfer things differently. All right, I think that's very important to understand why 4.0 and why industrial internet, why industrial value chain initiative in Japan, in US, in Germany, different. So let's look at Germany. I think Germany, obviously in 2011, 4.0 name was given based on many different discussions between industry leaders and also the government. But if you look at the why manufacturing transformation is needed in Germany, we have to look at the fundamental difference. Germany has a strong foundation in manufacturing based on two things. Based on first, hidden champion and apprenticeship, we call diploma program of education, right? So basically, this is a very important part of a German education, because the Mittelstand, we call this a hidden champion. There are several thousands companies in Germany. They make products based on their belief, and they give the know-how, the machinist or craftsman experience to next generation. Then they give to continuous pass on to next generation. Then the education system, same thing. Students learn things while they're in the school. Eventually, they can apply this knowledge to real world. Unfortunately, recent years, the apprenticeship program has changed. Germany now basically adopt the same system like the United States. You have a 4 years bachelor degree, 2-year master's, and eventually you can decide go to industry or to do a doctor of engineering. But so the 4.0 really is a new thinking, how to create IoT using big data, to create more evidence-based practices, to transcend traditional experience-based. So by doing that, you can see in 2011, when you look back, Germany has been one of very strong export country in mechanical machinery products. But if you look at 2011, way back 5 years, really the growth is not there. So that was a wake-up call for German government, right? So eventually you can tell why German government want to rethink how can they make the product become more valuable for customers rather to sell machine once and then people use it for a long time, because German machines are good. They last for a long time, sometimes 20 years. If a customer only buy a machine once for 20 years, you don't make too much money. So eventually 4.0 concept come out really to rethink. When IoT, when a industrial big data, when predictive analytics, when cyber physical system is a foundation, what can the manufacturing be? So they introduced the first generation, you can tell, based on the steam engine. Then eventually second generation industry revolution really start from Cincinnati, United States. Cincinnati has a strong German heritage, right? And that's 1873. And when you can tell this chart, 1873, when a typical a division of labor practices was used in Cincinnati, the peak production, you can say meat packing foundry. You can tell how the process are divided into different stations. Then the division of labor was used to process the processing. Eventually, the system became fully synchronized. That practice was in 1873. This also was the birth of second industry revolution. In 1923, Henry Ford adopted the same concept, but reversed that process. They take the small component, each step by step, assemble to a final product we call Model T. So basically, it's an inverse process of the Cincinnati production line in 1873. So this too, we can regard as a second generation industry revolution. The third industry revolution is about really smart computers, IT, and today's everything about automation. Everything we see today is about third industry revolution. Now, when we move to next generation, the question will be, what can we do to utilize machine learning and industrial big data and the industrial internet, eventually make the machine become more predictable, so the factory can more synchronize between supply chain and also the factory. So that is called the 4.0. So if we look at how Japanese is different, and obviously each country have their different philosophy. Japan really look at the industrial value chain initiative. The reason is, if you look at Japan traditionally, Japan's from strong SME and Keiretsu. Keiretsu really called a supply cluster system. For example, Toyota is a big driver. Then under Toyota, you have Denso, you have many other companies, Omron and Yamatake, and also many companies together. They work for Toyota, eventually make smart manufacturing and system. So that's called Keiretsu. Same thing, Hitachi, Toshiba, Sumitomo, Komatsu, each company have a big keiretsu. So, but the more and more so, when keiretsu is to build smart manufacturing from bottom up. But now when you look at the manufacturing to customers, how can I bring value to customers? Now, this is becoming new thinking. So in Japan, government's pushing for value creation initiative. When I sell the product as a function, how can I sell the value as a solution instead just function? So that's what Japanese is pushing as well. US is quite different because US, as you will know, in the United States, there are many manufacturing USA institutes, right? These institutes, including like digital design manufacturing and DMDI, and we also have robotics, also have a composite, lightweight materials. But eventually, these institutes also symbolize a new cluster of industry working together with a different kind of organization like universities to bring new ideas that combine with the new technologies to enable future manufacturing. But the foundation, US, does not just depend on this traditional manufacturing. The industrial competitive ecosystem always the driver of US innovation. This we call 6S system. What is a 6S system? Well, space, aerospace is always a very important piece of industry that drive lots of advanced manufacturing. Semiconductor, which is always in the frontier to drive a new and future electronics. Geogas, it create new energy system. Smart ICT, right, is including analytics and smart IT system. And Silicon Valley always a model of the relentless innovation and sustainable talent pool. We call unlimited talent from great immigrants. Those 6S system always drive a U.S. competitive, the industry roots. So these 6S's is very important for United States' growth. Now, so each country different. Now let's look at today what's the difference between 4.0 and today's factory. Why industry want to renew itself? All because today's technology create new processes that enable us to learn fast. Also enable our system can respond fast, right? So I define called 5-level productivity model. When early years, when we start pushing for automation and lean manufacturing, that's called hands-on level. We're trying to learn, we're trying to improve to be compete. Later on, we create NC, CAD/CAM, CIM, lean manufacturing, and Six Sigma. Those are data level because we have machine data now. From design, we can put in a post-processor, go to NC. And then we have data, we can analyze root cause. Then we can have data, we can design for Six Sigma. Those are for data level. Level 3, we call information level. We need those use data to create new control algorithm, new actions, new reconfiguration methodology to enable the system become smarter. The 4th is called knowledge level. The people who use the machine, who use the manufacturing, who conduct the business, they should be able to utilize advanced analytics to optimize for resilient operation, high performance, worry-free. Eventually, level 5, synchronized, which means we need some smart embedded system or predictive system or smart IoT, allow machine to machine, allow internet of fleet of system to connect together. If some minor things change happen, I can synchronize, predict, eventually optimize to avoid. So the system itself become very resilient. This is called 5-level productivity model. So when I look at this, then eventually we say what the predictive analytics become a driver of the whole system because without predictability, it's very hard to give the productivity. So we also look at the broad spectrum of the data role in manufacturing. Now, traditionally, we look at the data from machine, product, and people. So you can see from here, from machine to product, base is CAD/CAM, and from the machine to people, we use TPM, TQM, and CIMMS. Eventually, from product to people, we do design, CAD/CAM, CAE, and eventually become product lifecycle management. Now, from the system, we also have to connect to suppliers. That's for SCM, supply chain management. And then we also have to connect upper space to customers. So it's called CRM. So these are the connection of the data. We have to make this data become reusable and reconfigurable. And also, we can reinventing the new methodology. So this we call the data role. Of course, the upper level is connect to the market variation, where we consider reconfigurable manufacturing as a function to respond faster and how to scale the manufacturing system. Now, when you look at the manufacturing from McKinsey IDC reports, we can see that the manufacturing has the largest data in terms of value asset, right? So today, if we can analyze this data using a smart analytics, we will be able to create more evidence and more smart decision-making logics for future manufacturing. That's where we start thinking why manufacturing is the foundation for the future growth. Now, of course, you can see the from left side is all the data source from machine, from NC, from robots. Right side is all the business tool, right? ERP. Now, middle side is the word's lacking. We call the machine health analytics. Without that piece, all the data cannot be effectively utilized. So that is where the missing gaps are. So therefore, we look at the future evolution. How the future evolution can be uniquely different and than previous manufacturing. We can look back at 1980s, that quality was the major driver, right? At that time, we have TPM, called practice-oriented manufacturing, and also some technology developed to support that. 1990s, Lean and Six Sigma became the major driver. So we use a data-centric process to drive continuous improvements. Then 2000, then we start using a embedded systems, and we use a predictive, we call a prognostic and health management to drive product lifecycle management. At that time, we used many predictive tools to analyze a possible effects or root causes and to predict the possible issues. And 2000 later and 2010, we can see today more companies are driving for predictive analytics for customer-centric value creation. For example, if I can use a big data to help you to save fuel of your jet engine, to save fuel of your vehicle by using the tire information, then you can create more value than just selling products. Eventually, the predictive analytics, including IoT, machine-to-machine, and the cyber-physical system, digital twin, those are the today's technology. So by using this technology, we can see clear shift, right? The future manufacturing is using a predictive data, not just a data analytics. So this chart shows the difference between today's factory and the future 4.0 factory. We can tell clearly from component level, from machine level, from factory level, right? From component level, we're looking for precision. From machine level, we're looking at quality, productivity. And from production system, we're looking at efficiency. So you can tell 4.0 is about have a self-aware function, the degradation management from component level. Machine level, I can self-aware, self-compare. I can self-predict. And in production level, I can self-configure, self-optimize, eventually achieve worry-free production. I think that is a big difference between today's factory versus a 4.0 factory.